Okay, we're now ready to tackle the problem of conformations of six-membered rings. And this is, as I said in the previous lesson, is more complex than that of 3, 4, or 5-membered rings, and it's going to take 2 full lessons to cover everything we need to talk about concerning six-membered rings, or cyclohexanes. All right, so let's first consider what conformation a six-membered ring is going to want to adopt. Well, as you could probably figure out after going through our analysis of the 4 and 5-membered rings, planarity is not going to be the best bet for a six-membered ring. If a 5-membered ring with the interior angles of a pentagon being 108 does not adopt a planar conformation, it's going to be worse for a 6-membered ring because the interior angle of a hexagon is 120 degrees. Therefore, cyclohexane, if it were planar, would start to develop angle strain in the other direction. The angle would be forced to be larger than the 109.5 degrees angle that it wants to have. And furthermore, a planar conformation of cyclohexane would have an incredible amount of torsional strain associated with it because we're now talking about 12 hydrogens. Okay, so if planar is not the option, what are the reasonable options? Well, it turns out that there are 2 different conformations that allow for bond angles of 109.5 degrees. Okay, one of them is called the chair conformation because in this conformation the molecule kind of, if you go with me a little bit, looks like a chair, all right? This is the seat of the chair, this is the back of the chair, and these are the legs of the chair. In fact, more than the kind of chair that you would sit in a classroom, think about it more like a lounge chair. You're lying back on the beach, this is where your back goes, and this is where your feet go. Anyway, 1 carbon is up, 4 carbons lie in a plane, and the other carbon is down. That's the chair conformation. The second potential conformation is what we call the boat conformation. And the boat conformation is called that because, with a little imagination, it looks like a boat. Okay, the boat can float in the water. We have the bow of the boat, the stern of the boat, and we have the 2 sides of the boat. Okay, in this case, both the bow and the stern of the boat are both up compared to the plane defined by the 4 central carbons in the boat. Okay, and you can actually get a boat conformation from a chair conformation by simply flipping up the front legs of the chair. Okay, so if I start with a chair here and take these legs and flip them up, now I have a boat. So what you definitely need to do is get your models out and practice building cyclohexanes. It's not, the models are not even going to let you build a planar conformation. That's how much higher in energy it is than the chair or the boat. Now, chances are pretty good that on your first attempt you will come up with a boat, but if you come up with a boat, to get it to the chair, all you have to do is take the back or front of the boat and flip it downwards until we have a chair. All right, so the next question we have to consider is which conformation is lower in energy, the chair or the boat? The answer is the chair. And the reason for that is because the boat conformation has torsional strain due to the eclipsing of bonds on the sides of the boat. Okay, so let's hold up our model and look at the sides of the boat now. Okay, this is one side of the boat, and you can see that the CH bond on the carbon closest to me and the CH bond on the carbon closest to you are eclipsing each other, more eclipsing down here. On the other side of the boat, as long as we have a good, perfectly shaped boat, you will have eclipsing up here and eclipsing down there. Now, there isn't eclipsing everywhere. If you look at the carbons that contain the front and the back of the boat, those CH bonds are staggered relative to each other. Back of the boat, same thing. The CH bonds are staggered relative to each other. Now let's compare that to the chair conformation. In the chair conformation, no matter which CC bond I look down, which of the 6 CC bonds I look down, the CH bonds are all staggered relative to each other. Okay, staggered, 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 and staggered. Okay, so since there is torsional strain associated with the boat conformation and no torsional strain associated with the chair conformation, the chair conformation is lower in energy. We can see this also with Newman projections that we used for the acyclic molecules. Okay, so these Newman projections are a little more complicated. So what we're doing in this case is looking simultaneously down the 2 sides of the chair, okay? And then in the chair picture on the screen, you can see that the front carbon is down and the back carbon in between the 2 sides is up. And when you look at this Newman projection, you can see that everything is staggered. Yes, you have CH2s instead of CH3s or hydrogens, but the staggered relationship becomes very clear from looking at the Newman projection. For the boat, on the other hand, if we look at its Newman projection, it is easy to see the level of eclipsing that is going on between the CH bonds and even the eclipsing of the carbon-carbon bonds between C1 and C2 and C3 and C4 of the ring. Okay, so the energy difference, because of all of the torsional strain that's still there in the boat conformation, is sufficiently large that we're going to discard the boat as being a viable conformation and assume that cyclohexane is always a chair. However, that still doesn't completely describe the conformational possibilities of cyclohexane, because it is possible to undergo something called a chair-chair interconversion. When we use our chemical drawing program to draw these structures, you can see that there are 2 chairs that we get. I'm going to call them chair 1 and chair 2 for lack of coming up with anything better to call them. So we have chair 1 is a chair that's facing left, okay, kind of like this, and then chair 2 is a chair that's facing right. Well, I can convert chair 1 into chair 2 by lifting up the legs and putting down the back. Okay, so I have a chair that's facing to your right, and now if I lift up the legs and put down the back, I have converted that into a chair that is facing towards your left. Okay, if you just lift the legs without putting down the back, you get a boat. So a boat can be thought of as an intermediate between the 2 chairs. And we can do an energy diagram for chair-chair interconversion just like we did an energy diagram for rotation in ethane and butane. Okay, so go with me here. We can start with 1 chair and put that all the way on the left-hand side of the energy diagram. And then what we're going to do first, okay, we're going to start like this. We're going to lift up the feet. And that actually gives us what's called a half chair. That's really high in energy because half of this molecule is in the planar form, and you have all of this eclipsing and torsional strain. But then as we go higher, lift it all the way up, we end up with a boat. Now, a lot of diagrams in your textbooks actually talk about a twist boat. It's actually a little lower in energy for the boat to twist a little bit one way or the other because that relieves some of the torsional strain. That is true, but we're going to not discuss the twist in great detail and just assume that the boat of some sort, twisted or untwisted, is in the middle of this process of chair-chair interconversion. Then what we have to do is take the left side here and start to bend it downward, so we go through another half chair, and then finally when you bend it down all the way, you get to the other chair, which is also very low in energy. In fact, it is exactly the same energy as in the first starting structure. Okay, so this brings us to the topic of what are called axial and equatorial positions. Okay, so the two hydrogens on a particular carbon in cyclohexane occupy stereochemically distinct positions. So there are 6 hydrogens on cyclohexane that point either straight up, so 3 of them point straight up, and 3 of them point straight down. Those 6 hydrogens are called axial hydrogens because they point, if we think of the ring as being the equator around the Earth, these hydrogens point towards the axis that the Earth is rotating around. And then there are 6 more hydrogens that either point up and out or down and out. And since they're pointing out and located along the equator in this metaphor, they are called equatorial hydrogens. Okay, so axial hydrogens, as you can see both from the model and from the diagram, alternate between up and down, up, down, up, down on adjacent carbons. Okay, so in the diagram, the 6 axial positions are in red and the 6 equatorial positions are in blue. The equatorial positions also alternate between up and down, but for the equatorial, instead of saying up and down, I like to say up and out, down and out, up and out, down and out, up and out, down and out, to reinforce to you the concept that the equatorial positions are primarily pointing out rather than up and down. Okay, so then the important result that we get from equatorial and axial is that if you do a chair-chair interconversion, you turn all of the axial positions into equatorial positions and vice versa. Okay, so keep an eye on the carbon that I'm holding onto with my hand. If right now in this chair, it is occupying an axial position. If I do an interconversion of it, that axial position has turned into an equatorial position. On the same carbon, if I start by holding on to an equatorial position and I do an interconversion without letting go, I now have, I'm holding on to an axial position.